I really like this section because this is the first opportunity I have to explain to students why we do this weird progression in elementary school with our notation for multiplication. When you're in, oh, I don't know, maybe third or fourth grade, you learn that, for example, 3 times 4 equals 12. But then you get into middle school or high school and you start playing around with x's, and it's really easy to confuse 3x with 3 times. So we just say, well, let's just use a different symbol. We'll go 3 times 4 equals 12, and we'll use this dot instead of this cross. Well, it turns out that in algebra, in arithmetic, in the real numbers, these two things, these two symbols, do the same things to these two numbers. But in matrix algebra or in linear algebra, they do not. So in arithmetic, we can get away with just sort of moving from one symbol to another. In fact, at one point, we introduced the idea that we can use parentheses to get the same idea either there or on both of the numerals, right? And we do that because sometimes you want a negative in there. Anyway, there's multiple different ways to write a multiplication problem, no pun intended, in arithmetic, use on the real numbers. But in linear algebra, in the land of matrices and vectors, that's not the case. We have two different kinds of products of vectors. One of them is called the dot product, and one of them is called the cross product. And that's beyond scalar multiplication, where you just run a real number, scale a real number through the vector. The dot product is the simpler and I think easier of the two matrix or vector multiplications. So let's just take a couple of vectors here. So let's go with u equals, I'm going to go ahead and stick with this notation for now, since that's what your textbook uses. U equals 1, comma 2, and v equals 3, comma negative 1. The dot product of these two vectors, which we'll annotate this way, u dot v, u times v, but noting that the dot has a very specific meaning in this context. That's going to be the dot product of 1, comma 2 with 3, comma negative 1. And what that means, how you accomplish this, is you take each component one at a time, the first component in the first vector and the first component in the second vector, and you multiply them together. So here I'm going to get 1 times 3, and then the second component is 2 times negative 1. So I'll get 2 times negative 1. And once you've done that multiplication, you add them together. So this is going to give me 3 minus 2 equals 1. So in this case, the dot product of u with v is 1. And you'll notice that that is a number, not a vector. I can do this in any dimension. So let's do one in R3. This one's R2. This next one will be in R3. So let's take R, vector R is 1, 2, 0, and vector S is negative 2, 1, 5. Then R dotted with S is 1, comma 2, comma 0, dotted with negative 2, comma 1, comma 5, which ultimately is 1 times negative 2 plus 2 times 1 plus 0 times 5, which is negative 2 plus 2 plus 0. So in both cases, when we did this dot product, we ended up with a scalar, a number. In this case, the scalar was 0. That can happen. That's a real number. I'm going to do one more here. I'm going to borrow this space that I used over here to get started. I'm going to do one in R5. I'm going to say let's let vector A be the vector 1, 2, 1, 1, 0, and the vector B It's going to be -1, -1, 0, 1, 2. Then A dotted with B, and I'm not going to write it out this way this time because I don't have room for one thing, but I think you get the point, and I don't really need this step. In fact, here they're already more closely aligned component by component, so I'm actually going to do it that way. I'm going to have 1 times -1 plus 2 times -1 plus 1 times 0 plus 1 times 1 plus 0 times 2. So I'll get 1, I'll do it down here, 1 times -1 plus 2 times -1 plus 1 times 0 plus 1 times 1, and I ran out of room anyway, plus 0 times 2, which is -1 minus 2 plus 0 plus 1 plus 0. And when I add those together, I get -2. So the scalar can be negative. The point I was trying to make with this one really more than anything else was that I can do this with any number of dimensions. I can't visualize R5. I have no idea what things in R5 look like, but I can still do this operation. The result of a dot product is a scalar. That's an important thing to take away from this. One more piece of information that you need for this, from this particular little topic, is that I cannot find the dot product of U from above with, say, R. It does not exist because the dot product is a component by component operation. I can only do component by component operation if both vectors have the same number of components. So if I try to dot vector U, which is in R2, with vector R, which is in R3, I can't. I won't be able to do that because I don't have enough components in U to match all the components in R. Okay, and I lied when I said that there was only one more thing here. There is actually one additional piece of information I want to make sure I highlight, and that is that the notation used in your textbook to describe the dot product uses sigma notation. What they've got here is U dotted with V, and these are just generic U and V vectors, not my U and V vectors. These are very specific. This U, for example, might be U1, comma, U2, comma, and so on, all the way up to UN, dotted with V1, comma, all the way up to Vn, and they have to have the same dimension. The dot product is going to be equal to U1, V1, that product, plus U2, V2, the product of those components, plus all the way up to UN, Vn, and that's really kind of annoying to have to write out. So what we do is we use sigma notation instead to say that if you take all the UI, VI products as I goes from 1, so we're starting with U1, V1, and goes up to N, so we end with UN, Vn, that gives you the same thing. So all of this notation in your textbook means, this notation here, is this. And all that means is that for some generic vectors U and V, you do this component by component multiplication and add together the results. And that's the dot product. In the next video, we're going to take a look at the geometric representation of the dot product.